And so these are kind of the core tools that we employ in optimization. There's actually been a significant amount of research in a number of other things, which are not really new ideas, but I've seen popularity in the past 5, 10 years. So things like ADMM, coordinate descent, stochastic methods, projected Newton's actually a really old method. But so we're going to talk about those more, I guess, sophisticated or more newly popular methods in the remaining lectures in the class. But today, we're going to use our basic toolbox of first-order methods, second-order methods, and interior point methods to see how that actually can be used to solve a interesting class of problems. And so what we're going to see is that in practice, there's really no silver bullet for knowing what the right algorithm is to apply to any given problem. And we prepared the table for you guys that has kind of shows all the different facts about each of the algorithms and how they're applicable to different functions based on what the criteria function is, what the constraints are. And really though, in the big picture scheme of things, in convex optimization, we're always developing, or at least typically developing, some kind of iterative method. And so the trade-off is always between what is the cost of each of these iterations, and then how many iterations is it going to take for the method to converge. So these are kind of the fundamental things that determine which algorithm is more applicable. And then for applications, you may have an application with really big data, or you may have an application where you need a really highly accurate solution. A lot of times in statistics and machine learning, you have noisy data, so you don't actually need a highly accurate to machine precision solution. A approximate solution is good enough, sometimes even better in some cases. And so, with all these considerations in mind, it's never exactly clear when to apply each type of algorithm. And so, that's really why we've gone through all the material in this course to really help you understand the trade-offs and what's actually happening behind the scenes. And so we're going to apply this knowledge to problems of this form. So this goes by many different names. In these sets of slides, we're calling this the sum of norms regularization problem. And so here we have some smooth function, f. As usual, we have parameters or optimization variables beta. And we have some smooth function f. And then we're going to consider a class of regularization terms that have the following form. We take a sum over some number of groups j. And in this sum, there's a penalty matrix dj. We apply that penalty matrix to the optimization variable beta. And then we take some norm of that quantity and then combine with a regularization parameter lambda. So essentially, this is kind of the basic framework from a lot of the examples, all the lasso variations that we've seen. And we're going to go through some more of those kinds of examples as part of these slides. So first of all, let's just make it clear how this relates to the lasso itself. So if we simply take f to be least squares penalty, and we take d to be the identity matrix, and with one group j equal to 1, then we recover exactly the lasso penalty using the L1 norm. So as a very trivial modification, if we instead modify d to remove one of the columns and if you take the identity matrix and replace one of those columns with all zeros, then essentially we removed that dimension of the feature vector from the regularization term. And so we can do that if we want to have an unregularized intercept term, for example. So that's kind of a trivial modification. We're going to look at more. So as a kind of outline, what we're going to do is look at examples of that form. We're going to talk about some of the algorithms. We're going to talk about specific problems and actually data sets where you apply these algorithms. And then we're going to revisit and see how we apply first and second order methods and interior point methods to solve these problems and see what the trade-offs are. And so we're going to start this today. I'm going to get through as much of it as possible, leaving some of this stuff for Ryan when he comes back on Tuesday. So, I guess it's worth saying that none of this stuff I think is really going to be on the test or is any kind of it's really meant to give you guys intuitions and see how you actually use this stuff in practice and see kind of what the interesting computational and convergence issues are that come up. All right, so let's talk about another class of problems called the fused lasso problem, or total variation denoising. So in this case, we have a D matrix, and this D matrix is n-1 by n matrix, where we have negative ones on the diagonal, and we have 1 on the superdiagonal. So when we apply this matrix D to the parameter vector beta, we get the differences of adjacent terms in the beta vector. So that's shown here. We've seen this actually. You guys implemented this in the 1D fused lasso problem on your very first homework, where you essentially just typed it into CVX. So you've seen this already. I think you've seen it in other contexts as well. And so essentially what happens here, as you've seen in that homework, is we're regularizing the differences in the beta vectors. So no longer do we have sparsity, no longer are we promoting sparsity in beta itself, but now we're promoting sparsity in the differences beta I minus beta I plus 1. And so essentially that causes beta I to be equal to beta I plus 1 in many of the locations. Of course, depending on, as we saw in the homework, depending on how we set the lambda regularization parameter. Higher lambda is going to be more sparse, lower lambda less sparse. And so when we actually plot this, as we've seen before, you get a piecewise constant signal. And so on the left-hand side, this is essentially what you had in the homework, where you have Gaussian loss, where you have some input vector y, which is a bunch of points, and you want to capture some kind of signal that approximates these input points with this additional structure on the signal. And essentially that structure in this case is the piecewise constant structure. So this is what you've done already. I mean, this on the right-hand side, we can also consider an example where instead of having real valued y variables, we have y's in 0 and 1, in which case it may be more appropriate to apply something like the logistic loss. And so here we have, again, a piecewise constant signal with a different version of the f function, and we recover an approximation to the input data with a particular structure. Does this make sense to everybody? That you guys should be fairly familiar with this just because you've seen this in your first homework. We've talked about these examples quite a bit. All right, let's continue. So we can generalize this D penalty matrix by, instead of considering just differences between adjacent components of beta, we can think of beta as being associated with some graph, and then we can penalize the differences over this graph. And so here we have a D matrix where the number of rows in D is the number of edges, and essentially D corresponds to the incidence matrix for this graph. And so now we have this piecewise constant structure applied over this graph, and we expect many of the adjacent vertices in the graph to take on the same value. And again, we saw this, I think, in the very first lecture. And we have an image here. And so we're going to construct a graph, which is the 2D grid graph. By that, I mean we're going to connect each vertex to its horizontal and vertical neighbor. And then we're going to penalize the differences so that those neighbors are encouraged to be equal. And so we take an image that's basically a bunch of solid colors. We add some noise. We can recover the original image by imposing this structure and solving the total variation problem. Again, you've already seen this. Another example. So here we have some crime rate data where we have, I think this is in Chicago. Yeah. And essentially, we expect that the data will be smooth, have some locality in space. So we impose, in this case, the graph's not necessarily regular. We have some different topological graph for the regions, and we connect each region to its neighbor according to that map. And then, so we have a graph over different places. And then we solve this problem, we get a smooth version of the original data. Now, when I look at this, and I actually said this to Ryan, this looks like it's actually over smooth to me because you're losing some of the variation, for example, in the bottom part. And So it looks like you're doing too much smoothing, but again, it seems like a reasonable approach in general. All right, so that's the basic signal approximator case where you have some data and you're getting a smooth version of that data by applying the fused lasso penalty. So now we're going to consider a slightly more complicated scenario. Or I should say, when we get to the algorithms, we're also going to consider a slightly more complicated scenario where we have some vector of covariates or some matrix of covariates. And so here we're going to solve a regression problem. And when we solve this regression problem, we're not going to penalize the output of the regression as we've been doing essentially, but we're going to penalize the weights, the structure in the weights that correspond to the coefficients of the regression. So you can think of this as we're imposing some structure between the different dimensions in the feature vector. And so why would we do that? Let's look at some examples to make this clear. Oh, and then by the way, again, we can use either a Gaussian model, which corresponds to a least squares loss, or if we have a classification problem, we can use, for example, a logistic model, and that's shown on the second line. So here's a particularly nice example of where this model works. I don't know if anybody does neuroscience or neuroscience applications here. OK. Good. Well, I probably am going to completely misrepresent this, but I'll give you my understanding, essentially. What you do is you take an MRI, and you have a bunch of readings for each of the voxels in the brain. And then we're going to have a classification for each, in this case, whether each of the subjects has Alzheimer's or does not have Alzheimer's. We want to build a model that, based on these MRI readings for each of the voxels, we are able to predict whether or not the patient has Alzheimer's. Right? And so what we see in each of the different columns, so first of all, let me describe the graph going by column. So on the left-hand side column, we have a model that's been trained using this fused lasso penalty, where we encourage the voxels to take on the same value for voxels that are adjacent in space. On the middle graph and on the right-hand side, we have different models trained just with a simple lasso penalty, where we encourage learning a sparse set of voxels, but not necessarily to have this spatial property where they're encouraged to be similar. Now on the top, what we have is we actually train the model with cross-validation and evaluate the held-out error. We get the best model under some criteria, and using this best model, we identify what are actually the voxels that are predictive of the output condition, either having Alzheimer's or not having Alzheimer's. So that's shown in red on the top, and then in the middle, we see Now, of those voxels that are actually active in the model, which ones are actually correlated with the negative case of having Alzheimer's? And as I understand it, just from briefly reading the paper, essentially the region that's shown there is the hippocampus. And so that's believed to be where a region that's highly relevant for Alzheimer's disease. And so, but structurally, what we're doing is we've taken the problem from identifying just single voxels that are responsible for a condition to now identifying regions in the brain. And so, based on, from a scientific standpoint, that's more consistent with how we think the brain works. And so they also have data. They also have quantitative data that shows that this model produces better predictions. And so finally, on the right-hand side, on the far right column, we have the same number of voxels as on the far left column, but you can see they don't have this particular structure without imposing the fused lasso penalty. Any questions on that? So I think in this case, this is the actual model. This isn't an individual patient. And so the middle row corresponds to the features, the coefficients that are most predictive of Alzheimer's. And so for 3 different models. And yeah, I think the data is trained over several hundred people. All right, so we've talked about some problem setups. We have basically two scenarios. One where we have just a straight signal approximation case where we want to approximate a piecewise constant or some other structure in the signal given data. And then we've also talked about the more sophisticated scenario where we have a regressor matrix and we actually want to impose the structure on the coefficients, on the weights for that on that feature space. So now we're going to talk about how do we actually employ the optimization algorithms to solve problems of this form. So first, we can consider the subgradient method. And I think as we've talked about quite a bit in class, the main downside of the subgradient method is that convergence is slow. So it turns out that it's very easy to compute a subgradient in this case. In fact, we can ignore all the components of d beta, which are non-zero, and we just need to consider the active, so to speak, components. We just sum up over those components according to the definition of the subgradient. And so computationally, this is very attractive, right? Because we can compute this very quickly, assuming, of course, that you can compute the gradient of f, which for the models that we've talked about, it is not a problem. And so this is nice, but in practice, it doesn't work well for these problems because it takes many, many iterations to converge. OK, so then we've also seen a proximal gradient descent method. And in this case, what is the prox operator? So the prox operator is similar to what the prox operator is for the L1 norm. But instead, we now have a complicating factor in the D matrix, which is applied inside of the L1 penalty. And so essentially, this problem, the prox operator itself, which involves the proximal term beta minus z norm squared, that's essentially the same problem in many cases as the original problem we're trying to solve. And so we really didn't accomplish anything by just considering the proximal operator, at least for the primal problem. So OK, what else can we do? We can consider reparameterizing the problem by replacing the L1 norm with linear inequality constraints. And I think you've probably seen this in various places. And this is actually a reasonable approach in this case. The one downside is that in order to do that, you need to introduce a new set of variables corresponding to the absolute value of each of those components. And so we have actually twice as many variables to do that. But other than that, it's a fairly reasonable approach. And we could go along that path and derive an interior point method. Instead, what we're going to do is look at the dual problem as we often do. And in general, I think the point that should be emphasized is that when you have a new problem like this, it always makes sense to consider the dual problem and look at the structure of that problem in order to better understand the optimization problem. So this is the fuse lasso dual problem. And so basically, following very similar derivations that you've hopefully done several times now, we can derive this dual. Do people understand? Are people comfortable with how you do this? Or is it worth going over the actual derivation? Let me just ask a survey, understanding no one ever raises their hand. Is there anyone that would like me to go over this derivation? OK. Neil says yes. So I guess let's do that really quickly. It's actually assuming I can actually turn on the projector. Yes. Yes, but I'm trying to switch this one to the. No. I need my technical support from Dallas. I thought last time all we did was tap on the screen and it switched.
Yeah, I think so. I think you just hit this first.
Oh, that's fancy.
And this is up there too.
No, yeah, so it's perfect. Okay, good. All right, so the original problem that we had was right? And so in order to consider the dual, what we're going to do is introduce a equality constraint where we introduce a new variable, z. And set that equal to d beta. So really the dual, the reason we do this is if you don't have some kind of constraint, the dual doesn't make a lot of sense. And so essentially you need to have some kind of constraints which become the variables in your dual problem. All right, so then we're going to write down the Lagrangian. Let's just write down f over beta. And then, so in order to, sorry, lost my microphone. In order to form the dual problem, we're going to minimize this over beta and z, the primal variables. So just rearranging terms, we have minimize over beta. This is equal to plus u transpose beta plus minimize over z. Oops, that should be a lambda. Right, all I've done is move the terms around. All right, so now we essentially apply what we've learned about conjugate functions. And so we've seen before that this first term is exactly equal to the conjugate of f evaluated at minus d transpose u. Right? And that just follows from essentially what is the definition of the conjugate function. And so really, just as a side note, we haven't really done anything by doing that. We've just rewritten, we've just used a different notation to go from the first to the second term. But in general, this notation is very useful, and it's useful to think about the conjugate functions when you're considering duality. All right. So and then we have, and so then for the L1 norm, we have to consider what's the conjugate of the norm. And we've seen that the conjugate function for the norm is related to the dual norm. And in particular, that for any norm, the conjugate function is the indicator of the ball for the dual norm. And so you've seen that, at least in lecture. If you're not familiar with that, it's probably something that you should review, because I think it comes up all the time in convex optimization. So in particular, we have this is equal to minus indicator less than or equal to lambda. And so in terms of the lambda term, basically I use the identity that if I have some function f star y, and then let's say I have a f of x, and then I know how to compute the conjugate, oops, sorry. I have some f of x, and then I instead want to consider lambda f, right? So we have a slightly different version. The conjugate of that is just going to be 1 over lambda f star, right? So it's just a basic identity that follows from the definition of what the conjugate function is. So using that, we can so in order to set up the dual problem, we're going to maximize this over u greater than or equal to 0. And so in particular, we're going to have that this is equal to, by convention, we just rewrite that as a minimization problem, and that's minimize d transpose u, subject to, sorry, this is u. Or sorry, no indicator in the constraints. Subject to u is less than or equal to infinity, right? And so now we're done. That's exactly what we have written on the slides. So hopefully that makes sense. Any questions on that? Yeah. Yes, yeah. And so in this case, you mean up here? Yeah. You're right. Yeah. I meant, yeah, it should be inside. Sorry. F star 1 over lambda. Hold on, let me think. Right. So in this case, yeah, you have to bring it's not 1 over lambda. You have to bring the lambda out. But in this case, if you have a constant scaling times the indicator function, it's the same thing. So you can drop that term. Yeah, that's right. Thank you. All right. And so then using the same techniques that we've seen numerous times, we can look at the KKT conditions for this problem. Sorry, where's my clicker? And so the KKT conditions, so first of all, if we differentiate the Lagrangian with respect to beta, then we have this condition here, which basically gives us how we can recover beta from the dual variable u. So that's useful. So assuming that we have a simple expression for the gradient of f evaluated at beta, then we can recover the dual variable, the primal variable from the dual variable easily. And also we have if we differentiate or take the subgradient, consider the subgradient of the Lagrangian with respect to z, then we have the conditions we have further conditions on the dual variable u. And essentially these conditions are interesting in the sense that we see in some sense, the sparsity in u is reversed compared to the sparsity in the primal variable z. And in particular, whenever z is 0, then so u is not sparse, but I'm using sparsity in a kind of general way, so in the sense that whenever u is at one of the boundaries, lambda or minus lambda, I'm calling that sparse. But in any event, when u is at the boundary, that's the opposite. That happens at for the coordinates at which z is in the interior of the L1 norm. So when z is non-zero, and when z is 0, then u is in the interior of the constraint. So in some sense, the sparsity pattern in u is opposite that of the primal variable z, and essentially that's what the last line is saying. All right. All right, so now we have the dual problem. And so now let's consider what the proximal gradient descent method looks like applied to this problem. And now because the key observation is that by considering the dual in this problem, we've moved the D matrix from the non-smooth term to the smooth term in the objective. And so because of that, now we can define a simple proximal operator for the constraint term, and that proximal operator is just given by projecting the variable onto an m-dimensional box, right? So so basically you just take the variable, and if the variable is larger than the absolute value is larger than lambda, you set it equal to lambda with the appropriate sign. Otherwise, you leave it the same. So it's a very simple proximal operator, as opposed to the proximal operator for the primal problem, which was essentially as complicated as the original problem. Does that make sense to everyone? All right. So that's good. We have a proximal gradient method, and we can even use acceleration to make this proximal gradient method faster. But in some, for reasons that we'll go into in a few more slides, briefly, anyways, we may want to consider a method which converges in fewer iterations. And so it turns out that in practice, not unlike what we saw in the homework with the MNIST example, it can take many iterations for the proximal gradient method to converge. And so in order to deal with that, let's also consider an interior point method applied to the dual problem. And so in order to apply the interior point method, we're going to rewrite the constraint slightly. And so that instead of the infinity norm, we have UI, we have two linear inequality constraints. And using that, we can write down the log barrier for those inequality constraints. That has a simple form shown here. And so now we're going to consider applying Newton's method to the dual problem with the constraints moved into the objective function by virtue of the log barrier. So this is just the standard thing that we've done in the past with applying the log barrier to optimization problem. So the key question for any Newton method is really how efficient are the Newton updates. And so in general, if I have n variables, how many flops does it take to compute a linear system in the Hessian if I don't take advantage of structure? Yes. So in general, it's going to take n cubed, right? And so it turns out that for this problem, because, if I can go to the next slide, it turns out that for this problem, we didn't even write it on this slide, but it turns out the upshot is that for this problem, in many cases, we can actually solve a linear system in the Hessian in order n flops. And so that's pretty unique, actually. And so because of that structure, then we can actually derive a very efficient interior point method. In fact, we can derive an interior point method that is the same, basically the same per iteration complexity as the gradient method, and that is order n flops. So let's see why that is. So again, we have the function that we're going to apply Newton's method to, and then when we write down the gradient and the Hessian in general form, essentially what we get is, if we consider the second equation, what we get is the Hessian of the conjugate function of f with d and d transpose on either side. And then we also have the Hessian of the log barrier. So the log barrier in this case has a very nice structure. And in fact, the log barrier the Hessian of the log barrier is a diagonal matrix. And that happens just because the log barrier is defined in terms of an element-wise function in each of the coordinates. So when you have a function like that, you consider the Hessian, then you'll always have a diagonal matrix, assuming that it is twice differentiable. And so given this structure, depending on, of course, what the actual function is in the f star, we can expect to have a very efficient method for solving for the Newton step. And so let's see in more details. So I guess in the next few slides, what we're going to do is look in more concretely for the actual functions that we care about in these examples, what that looks like. All right, so to summarize, though, we talked about 4 different approaches to the problem: the subgradient method, easy iterations, slow convergence, proximal gradient method, unclear how to actually even solve the prox operator efficiently. The dual proximal gradient method, easy iterations, moderate convergence. And then I've argued at a high level why the dual interior point method could be very useful for this problem. And we just went over that. And so let's see. OK, so let's make this a little bit more concrete. And let's talk about, in particular, the fused lasso problem. So fused lasso problem is where the D matrix is just that first order differencing operator. And we're taking differences of beta I and beta I plus 1. And then we're also going to talk about either Gaussian or logistic signal approximation. So in this case, we have no regressor matrix. We're just approximating the signal directly with the parameter vector beta. And so as we've kind of argued for in the past, when we looked at, for example, the image problem, we've argued that we want a solution with a fairly high amount of accuracy. Otherwise, you get artifacts when you run the denoising problem. And so for that reason, obviously the primal subgradient method is out, and we've already said the primal proximal gradient method doesn't make a lot of sense. So in terms of the dual, so we're going to consider the dual methods. That's first we need to check that we can form the conjugate function, and that's a straightforward exercise for both of these functions, and it takes the form shown here. So that's good. These have a fairly simple form. And so now, and then we also need to check that given the KKT conditions, how do we recover the primal variable from the dual variable? And that's shown here. And again, it's a fairly simple derivation to do these things. And all right, so now here's the argument that I was alluding to a few slides ago. Why does it take a large number of iterations for proximal gradient to converge on this problem? So it turns out that when you have first order methods, such as the proximal gradient method, they're highly dependent on problem scaling factors. And essentially, what is the scaling of the linear operators, the matrices involved in the problem? And so here we show for the D matrix. So this is a D matrix actually, I guess, computed for the 2D grid. We show that as we increase the number of nodes in the graph, then how the condition number of the differencing operator increases. So actually, so in terms of how you interpret this, basically a higher condition number is going to require more iterations of the proximal gradient method to converge. And so this is for the 2D grid graph. It actually turns out that for the chain graph, the chain graph in the same number of variables, the condition number increases even faster. So in some sense, the D matrix can be somewhat poorly conditioned, especially for larger problems. And so, all right, so then let's proceed and talk about, with that in mind, let's proceed and talk about how we can actually apply the dual interior point method that we talked about. And so first of all, let's write down what the Hessian is for the two loss functions, the Gaussian loss and the logistic loss that we talked about. So for Gaussian loss, the Hessian is just the identity matrix. Doesn't get much simpler than that. And then for the logistic loss, you can show that the Hessian is a diagonal matrix with the following form. And so the upshot is that in order to compute the Newton direction for the interior point method, we just need to solve a linear system shown here. And this is the basic thing that you have to do to compute the Newton step in any problem. You solve for the direction that minimizes you solve for the Newton direction that minimizes g in the negative direction of g with respect to the Hessian. And so, as we've argued, or as I mentioned for the D matrix, because we have this structure in D, we can actually compute. So in the case, so let's take, for example, the case where we use the Gaussian loss, then the A matrix is going to be the identity. So this is D transpose plus a diagonal matrix. And so in this case, it actually, for any graph, essentially what the main computational expense is solving a linear system in the graph Laplacian operator. And so essentially what you have is D transpose D is the graph Laplacian. And in order to solve for the direction, you need to solve a linear system in that operator. And it turns out that can be done in, let's see, Ryan wrote close to order n flops. It's actually order n times the log m, where m is the number of edges. And so yeah. Say that again?
Is that a Fourier method or primordial interior
Is that a barrier method? Yes. So the way that so this is we applied the barrier method. You could do a primal dual interior point method. Be somewhat different. Yeah. So what we did here was we took the primal problem, converted it to the dual problem, and then constructed a barrier method for that dual problem. So yeah, this is the barrier method. All right. So let's go on to the next slide. So we've seen this graph before, and we actually saw this graph or this image on the first day of class. And I think probably for people who haven't seen this before, it's quite mysterious then what was going on. And hopefully now giving you some intuition for what the difference is between these two sides. And so, as I said, what's kind of remarkable for this problem is that usually interior point methods are far more expensive, as we heard, n cubed for each iteration. In this problem, the actual iterations are roughly comparable, and so with 10 iterations of one method, we converge to a highly accurate solution, and versus 1,000 iterations for the dual proximal gradient, we have an image. It's kind of hard to see on the projector, but essentially, this image doesn't look nearly as good as the solution on the left-hand side. All right. All right, so I think we'll take a 5-minute break now, and then after the break, we're going to talk about problems, what happens to the problem when you actually add a regressor matrix X.